In Australia, 4.4 million people live with a physical disability, with 1,800,000 people employing commercially off-the-shelf wheelchairs and powered wheelchairs. These devices generally operate through physical control through the user's hands or with a joystick. However, individual symptoms can vary in severity and consistency, with up to 40% of users finding normal operation difficult or near impossible, therefore rendering the benefits of mobility devices inaccessible for the entire spectrum of disabilities where a user's upper extremities are severely affected. Hi, my name's Hao Nguyen, and I'm presenting my undergraduate thesis topic, Enabling Autonomous Navigation for Existing Powered Wheelchairs in Urban Environments, with my supervisor, Dr. Ali Haider Gurktwan. So, what can we do to enable people with severe disabilities who cannot use a powered wheelchair joystick to travel independently? Presenting Swan, your smart wheelchair assistant for autonomous navigation. Swan is an add-on device for existing powered wheelchair platforms that provides an alternative set of control modalities. Swan is highly beneficial to users with different levels of disabilities and addresses the constraints of singular joystick control. Swan's system architecture consists of 5 main modules: the main control unit, obstacle detection, joystick controller, speech control, and the mission planning and teleoperation application. Swan is contained within 3 component enclosures. The primary enclosure houses the main computer unit, RGBD camera, and is mounted under the armrest, with the joystick controller positioned on top of the joystick unit. The second enclosure is placed on the footrest, containing front-facing ultrasonic sensors and a 2D LiDAR. Finally, the third enclosure is placed on the back, with rear-facing ultrasonic sensors. The selected powered wheelchair is powered by two 12-volt, 18 ampere-hour deep-cycle absorbed glass mat batteries. These batteries offer long service and often require no maintenance throughout their life cycle. Subsequently, Swan is connected to the batteries to power all of its components. An emergency button is placed in series between the batteries and Swan as an additional safety measure during field experiments. Accessing the mission planning and teleoperation graphical user interface requires an active internet connection. Both the MTT application and the backend server are enabled within a Node.js runtime environment. The MTP application is developed with React.js and the server with Express, a minimal and flexible backend framework. As the MTP application is web-based, it is easily accessible on any device such as computers, tablets, or mobile phones. Additionally, the server also handles incoming requests for the speech control UI from Dialogflow and Raspberry. Dialogflow is hosted on the cloud, and Raspberry is run locally on Swan within a Docker container, encapsulating all required dependencies. The server acts as an intermediary handler for incoming and outgoing requests to simplify communication streams before passing data directly to ROS, a middleware framework utilized for abstraction and process management of hardware and sensors. ROS operates locally on board Swan and communicates directly with low-level peripherals programmed with Arduino. Control algorithm development for Swan is completed with MATLAB Simulink and its ROS toolbox. The ROS toolbox allows easy abstraction of high-level control algorithm development, which is automatically generated into C++ code for deployment on physical hardware. Additionally, it supports external mode, which connects to a live ROS network for real-time monitoring and debugging during physical hardware deployment. On the graphical user interface, users can define a series of waypoints. Each waypoint can be dragged or deleted and execute user-defined actions such as stop, pause, or continue upon arrival. Line segments between each are configurable for desired speed. Saving and loading of missions is available from the local server onboard Swan or a remotely hosted server. And sensor data logging can be initiated with operational parameters such as default speed, maximum path deviation, and PID gains also configurable. To enable control for Swan, first the kinematic model of a powered wheelchair is derived. The following equations, which we unfortunately do not have the time to explore in depth, relate the linear and angular velocities of the wheelchair to changes in pose within the world frame. To initiate powered wheelchair control, on the joystick unit is a 3D printed detachable joystick controller with 2 servo motors. Joystick actuation is initiated from the servo motors with angular displacements proportional to wheelchair linear and angular velocities. Here we see Swan autonomously navigating a predefined path through Cattergall Green at the University of Sydney campus. The route is initiated and defined through the mission planning and teleoperation graphical user interface. Path tracking for autonomous navigation is enabled through the Pure Pursuit algorithm. The equations here derive how Pure Pursuit geometrically calculates the curvature that moves the vehicle to the desired goal waypoint. Its operation is quite analogous to how humans look ahead at certain distances to track roads while driving. To validate performance, over 4 kilometers of field testing was conducted at Cadigal Green to evaluate Pure Pursuit onboard Swan. Cadigal Green features footpaths of 2 to 4 meters width and presents several features that powered wheelchairs frequently find difficult to traverse. Sharp turns and large curved sections with varying sloped gradients. Field tests at Cadigal Green demonstrate effective handling and navigation against various footpath characteristics. Further verification was required for longer missions, better representing daily use case scenarios, with a 515-meter mission through Victoria Park. Victoria Park presents additional challenges compared to Cadigal Green, with constantly changing path widths of 2.5 to 4 meters, inconsistent path smoothness, increased gradients, and a bridge crossing. The longest mission achieved with Swan is a 1.2 kilometer mission through Victoria Park, demonstrated without human intervention. Teleoperation is available for users and caregivers through a virtual joystick, offering less physically demanding control. In the top right-hand corner, you can see that live RGB or RGBD video streaming is selectable and adjustable based on available bandwidth, given that a human operator can still discern obstacles at lower resolution and frame rates.
Going forward.
Additionally, speech control allows user operation through the recognition of several command types, for example, navigational commands.
Turn right 45 degrees. Turning right. Going forward.
Speech control is enabled through a dual speech processing architecture featuring 2 natural language platforms, Dialogflow and Raspy. Dialogflow and Raspy are enabled simultaneously, and the service with the highest intention detection confidence executes user intention. This prioritizes better performance, employs redundancy for safety, and ensures functionality outdoors, as Dialogflow requires stable internet connectivity for cloud processing, unlike Raspy. 13 speech commands spanning directional, rotational, mission initiation, and operational updates are each tested for 30 repetitions. On average, Dialogflow and Raspy demonstrate similar performance, however differences on certain commands were observed. For shorter commands, Raspy performs marginally better than Dialogflow. For longer directional and rotational commands, Dialogflow is notably higher than Raspy. Therefore, results demonstrate the strengths and weaknesses of both natural language services and support the design choice to prioritize execution based on intention confidence, given varying performance across different speech commands. Obstacle detection maximizes user safety to avoid pedestrian and obstacle collisions during navigation. The sensor field of views for the 2D LiDAR and ultrasonic sensors are configured for maximum coverage. Subsequently, safety regions are constructed for safer operation, with 3 regions indicating the obstacle proximity, initiating speed adjustments or an emergency stop if triggered. Experiments with obstacle detection involved placement of pedestrians in the middle of footpaths during autonomous navigation to observe Swan's behavior. The resulting speed profile and detected obstacle distance is indicative of safety region effectiveness, and is depicted here with clear decreases in speed observed as obstacles enter each corresponding region. Swan has validated its capacity to facilitate independent travel for people with severe disabilities who are unable to use the joystick of a powered wheelchair. Autonomous navigation and obstacle detection is demonstrated through high-density pedestrian environments. Mission planning and teleoperation is available through the GUI with integrated speech control, and future work with Swan will focus on the integration of additional control modalities, in particular gaze tracking. With new doors open for people whose options have always been limited, hopefully sometime in the future you'll see Swan out near you.